Now for sections 3.1 and 3.2, we're going to look at the graphs of exponential functions. So we have our basic parent function here, y equals a to the x. We want to graph in the same coordinate plane. F of x equals 2 to the x and g of x equals 4 to the x. You can honestly just put y equals is fine. And we're going to use Desmos to look at this first. Desmos is a lot handier on this because let me sorry about that. I think I got it straight now. So if we say y equals 2 raised to the x power, it gives us a pretty good graph to look at. And you should notice that it comes in right here with a y-intercept, but it does not give you an x-intercept, and it goes way up here really fast. Okay, let's go back to the home screen. Now let's look at y equals 4 to the x. These are the two things that I asked you to graph, or the book asked us to graph. However, I want to look a little deeper than this, okay? So I encourage you to pause the video right now and just pick numbers to be your A, to be your base, and go to the x power. Now, we'll point out back in our notes that when we learned about exponential functions, A has to be greater than 0 and A cannot equal 1. And that's a question I usually get when we're at this point because people forget that we did that. So if you did what I asked and graphed several different things, let's look at a few of them. Y equals, let's do 10 to the x. How about y equals 50 to the x? It just keeps getting steeper and steeper. You can go far enough that it looks almost like a right angle. How about, we know it can't be 0, we know a can't be 1, but it can be in between. How about y equals 1/2 to the x? Well, what happened there? Turn my graph around, right? Because 1/2 to the x power, all of my fractions are flipped over, okay? It also could be represented by, and we talked about this a lot in class, y equals 2 raised to the negative x power. So these two graphs, 1/2 to the x and 2 to the negative x, are the same thing because it's just two different ways to write the same thing. All right, back to our notes. Give yourself a little sketch here. We should have noticed that both of these laid close to the x-axis on the negative side, crossed the y-axis at 1, and went straight up. This was 2 to the x. But 4 to the x did so, sorry, that was a little much, laid on here a little bit longer, and then crossed over there. So they get lower on the left, and they rise faster on the right, the higher the base is. So this was 4 to the x. Okay? And we're going to talk more about that in a little bit. We just looked as well at 2 to the negative x. So 2 to the negative x still crossed at 1, but it came down from the left and then laid against the positive side of the x-axis. What do you think 4 to the x would do? Go graph it. It comes in a little steeper here and drops a little quicker there. So this is 4 to the negative x. This is 2 to the negative x. Sorry, I didn't color code that right. Now we're going to talk about our e. Okay, this 2e to the 0.24x. Sorry, I have to use the right tools or this doesn't work. Let's try it again. Y equals. We're going to go to the alphabet and get e. Oops, there was a 2 before that, wasn't there? E raised to the 0.24x. There we have it. Well, hopefully you're noticing that it didn't cross at 1. Let's try the next one. Y equals 1/2 e to the negative 0.58x. So y equals 1/2 e raised to the negative 0.58x. This one doesn't cross at 1 either. Why not? Well, looking at my graphs, for the first function, if I plugged in a 0 for x, which is how I get my y-intercept, I would have 2 times e to the 0.24 times 0, which is 2 times e to the 0, which is 2 times 1, which is 2. So we crossed at 2 here, and because it's e to the x, we still came in like an exponential function. 2e 0.24x. Whereas here, e to the negative power, we know comes in the other way. If I did 1/2 e to the negative 0.58 times 0, that's 1/2 e to the 0, which is 1/2 times 1, which is 1/2. So we crossed down here at 1/2, and we came in from this side because it was a negative power. All right, so that's the graphs of exponential functions. We will work on logarithmic functions in our next